Mechan 2410, Engineering Materials, Tutorial 3, Defects. We know that nothing in this world is perfect. So how about materials? Yes, there is no perfect atomic arrangement, even within crystalline solids. Defects, which represent the imperfection of these arrangements, atomic arrangements, which are also very important factors when we determine our materials properties. The definition is crystalline defect and imperfection is a lattice irregularity having one or more dimension on the order of an atomic dimension. The example here shows one defect within this crystalline solid, which is actually green boundaries, which I will introduce in later slides. It is because even though they have a same atomic arrangement, but at different regions of this material, the atoms are arranged in a different orientation, which represents the imperfection of atomic arrangements within these crystalline solids. Here is a list of defects: point defects, line defects, area or planar defects, and volume defects. Tutorial 3, Part 1, Point defects. There are 3 types of point defects: vacancy, interstitial, and substitutional impurity. And you can see here, vacancy is represented by missing of atoms that should be at here. Interstitial impurity represents addition of other atoms in the spaces between the normal atoms. Substitutional impurities means that another atoms substitutes for the original black atoms in this case. Vacancy is a missing of atoms in a regular lattice system. The existence of vacancies is a direct result of second law of thermodynamics. Using the definitions from statistical physics, S is equal to K times ln omega. S is the entropy, and K is a constant, which in the name is Boltzmann constant. Ln omega. Omega is the number of possible states under a given amount of energy. Let's consider a 9-atom case. Consider 9 atoms versus 8 atoms plus 1 vacancies arranged in a 3 times 3 square. And clearly that 8 atoms plus 1 vacancies has a more possible arrangement, and which is shown in the demonstration here. And that's why, as we know that the entropy of a system tends to its maximum value, and that's the thermodynamic evidence why vacancies must exist even in materials. And that's why for material it is more likely for them to have a vacancies than don't have any vacancies at all. And if you want to know more about this statistical physics, you may take Physics 454, which is thermal and statistical physics. There is an equation which can be used to estimate the vacancy numbers. Number of vacancies, NV over the number of potential sites, which is the number of the atoms, N, is equal to e to the power negative QV. QV is a constant, which is the activation energy for formation of these vacancies, over K. K is the Boltzmann constant, and times T. T is the temperature in Kelvin. Here's an example. Calculate the number of vacancies per unit cubic meters in gold at 900 degrees Celsius. The energy for vacancy formation is 0.98 eV per atom. Given that density and atomic weight are 18.39 gram per cm cube at 900 degrees Celsius and 96.9 gram per mole respectively, Boltzmann constant is equal to this value. We use the equation introduced in last slide. First thing we need to do is convert the units. As 0.98 eV is equal to 0.98 times 1.6 times 10 to the power negative 19 joule. 900 degrees Celsius is equal to 900 plus 273 Kelvin. And the Boltzmann constant K is in terms of J per K. And EV is defined as the energy needed of one electron moved across one loop potential difference. Therefore, 1 EV is equal to the electron charge value, which is 1.6 times this power times 1 moved, which is numerically exactly as 1 electron charge. Step 2, we need to calculate the number of potential sites, which is equal to the number of atoms. Number of atoms per cm cube is equal to the density times the Avogadro constant, which is the number of atoms within 1 mole of that atom, over the molar mass. And it is equal to this value. And then we just plug in the value, and we get that the vacancy number is equal to this value. Be careful of the units, as we have already converted the units, so we can just directly plug in the values. And we still have to convert the units for the answer, because the question requires us to provide a per m cube answer, not per cm cube answer. As 1 per cm cube is equal to 100,000 per m cube. The answer is this number of vacancies per m cube. Substitutional impurities, which the impurity atoms replace or substitutes for the host atoms. For example, zinc in brass. Brass is an alloy made of zinc and copper, which is also, you can also see in the picture here. Interstitial impurities. Impurity atoms add to the host atom matrix, but it do not replace the original atoms. Example, carbons in steel. Steel is an alloy of carbon and iron, and you can see the schematic here. The red atom, which is the additional impurity atoms, is only in the spaces between those original atoms. For metal, when small amounts of B is the solute, is added to A is the solvent, on purpose, which change the mechanical properties. B is called the alloy addition. Criteria to consider substitutional impurities. For it to be a substitutional impurities, the atomic size must be similar size, plus, for example, plus or minus 0.15% of the solute atoms, which will imply substitutional. If the impurity atom is much more smaller, then it will imply that the solute atoms, or not solute atoms, the impurity atoms will form interstitial impurities. Crystal structure. Same crystal structure will have a better solubility of the atoms. Electronegativity. For similar electronegativity, they will form substitutional impurities. Valence. It has a higher tendency to dissolve a higher valence metal. than a lower valence metal in terms of those impurities.